In this model, you will be able to learn about what is a logit and a probit model and when it is useful. We would also be able to understand the difference between logit and probit models, also about the estimation of logit and probit models, and we will try to find out how marginal effects and logit and probit models are estimated, and in the end we will discuss about goodness of fit and learn about them. Let me introduce this subject to you. Many times our dependent variable in a regression model will not be continuous. One of the types of such qualitative models is a binary response model in which the dependent variable y is a binary random variable that takes only the values 0 and 1. For example, our dependent variable can be whether a person gets a job from the college, which can be denoted as 1, or do not get the job from the college, notated or denoted as 0. Another example could be a situation where our dependent variable can be abnormal blood pressure, noted as 1 or denoted as 1, and normal blood pressure, which could be denoted as 0. The econometric problem is to estimate the conditional probability that gives y equal to 1 as a function of certain known explanatory variables denoted as probability of y equal to 1 given capital X equal to small x or variable x equal to a particular value of x, which can also be written to be a function of beta 0 plus beta 1 x. The functional form f should be such that y lies between value 0 and 1 for all possible values of beta 0 plus beta 1 x. It means the value should be between minus infinity to plus infinity. Such binary response models can be modeled using ordinary least square methods, and the same is known as linear probability models. So we can write these linear probability models by pi I equal to beta I x. The OLS estimation in case of this binary response dependent variable is very straightforward, and the interpretation of the coefficient is simple. However, it is computationally simpler. Marginal effects can be explained easily and the ambiguity over f is not there. At the same time, there are some issues with this OLS estimates. These estimates are not constrained to the unit interval, as the predicted value can be greater than 1 and less than 0. OLS estimation imposes heteroscedasticity in the case of a binary response variable. According to Horace and Saka, 2006, the OLS estimates in case of binary dependent variable are biased and inconsistent estimates. Also, you can refer to Amemiya 1977. The heteroscedasticity issue can be overcome by using heteroscedasticity consistent robust standard error estimates. Biasness is also not a big issue, as MLE or maximum likelihood estimation estimates of logit and probit, which would be explained further, models used for modeling such binary response variable are also biased in finite samples, but they are consistent. So given the sample sizes that we usually work with when modeling binary data, it is consistency and asymptotic efficiency that are of prime importance. Again, Horace and Okasa shows that biasness and inconsistency increases as the predicted probability fall outside the unit interval between 0 and 1. We have a graph which is obtained using a simple OLS framework. The data set is of patients suffering from diarrhea. Data contains a binary variable, which is hospitalization, and admit equal to 1 and not admit equal to 0, and the age of the patients. It is a hypothetical data set, and is given at the end in the appendix, and you can refer those who are interested to look at the data set in more detail. This graph basically shows we have the hospitalization of diarrhea patients versus age. We have age on the x-axis and patients who have diarrhea are on the y-axis. So we have the values which could be 0 and which could be 1. So 0, as pointed out earlier, is for those who are not admitted to a hospital, and 1 is for those who are admitted to the hospital. If you look at the fitted value, we find by OLS the fitted value comes out to be a straight line downward sloping. The probability of hospitalization of patient suffering from diarrhea decreases with age. The problem with OLS estimation is the predicted probability is higher than 1 at low ages, and it seems that at higher age the probability will become negative if you stretch or extend your this OLS line, which is the line of best fit. So you can see the left hand end of this line is above 1, and if you extend it, as I said, the line may go the x-axis on the right hand side. Now this points us towards another issue with OLS estimation, that is the probability increases or decreases at constant rate. Horek and Okasa 2006 even suggest that some kind of trimming rule that excludes the values which is making the predicted probability to go outside the unit interval can make OLS estimates unbiased and consistent. However, the OLS estimates may be consistent, and the logit and probit models, they help in overcoming many of the shortcomings in the OLS model, but it imposes a strict distributional assumption, violation of which may lead to biased estimates. So let us try to understand what are logit and probit models in this sense. Logit and probit is based on a latent variable model, which could be written as one of the first could be probability yi is equal to 1 given x, which is equal to probability yi greater than 0 given x, which can also be written as probability yi equal to 1 given x equal to probability xi beta plus epsilon I greater than 0 given x. On manipulation, this can be written as probability yi equal to 1 given x equal to probability epsilon greater than minus xi beta upon x. So we have taken the negative values of both of them, and or in a way you can say that we have kept epsilon on the one hand and xi beta we have shifted to the other side. Now this equation is same as probability yi equal to 1 given x equal to 1 minus f minus xi beta, or f of minus xi beta, which can also be written as probability yi is equal to 1 given x equal to function f of xi beta. Here f is capital F, which is nothing but the probability distribution function. The logit and probit models differ in their choice of this f function of xi beta. In case of logit model, the fx is a cumulative logistic distribution given by a function fx equal to 1 upon 1 plus e raised to power minus x, which is equal to e raised to power x upon 1 plus e raised to power x. And the corresponding probability density function, which is given by small fx. So I hope all of you understand that the density function is written by small fx and the cumulative function is written by capital Fx. So small fx, or the density function in this case, is equal to e raised to power minus x upon 1 plus e raised to power minus x whole raised to power 2, or it is the square of this entire denominator. In case of the probit models, the fx, or the cumulative normal distribution, is given by fx, capital Fx. This capital Fx is equal to x is equal to half plus in the bracket 1 plus ERF in bracket again x upon under root 2 and the whole bracket closed. And the corresponding probability density function is given by small fx, which is density function, is equal to 1 upon root 2 pi e raised to power minus x square by 2. So we have this graph in which we have the normal and logistic cumulative distributions. We have one for normal, the second is for logistic. And I am sure you can observe now on the x-axis we have the values of x, and on the y-axis we have capital Fx, which is the cumulative distribution function. And we have the corresponding graphs, which is based upon 10,000 observations. The graph above gives the cumulative logistic and normal distribution. The logistic distribution gives a higher probability in the beginning. That is because the logistic probability density, which can also be seen in graph, has fat tails in comparison to the normal distribution. Let's now look at graph. And in this graph, we have the normal probability distribution and we have the logistic probability distribution. And again, we have on the x-axis the values of x and the values of fx on the y-axis, which is also again based on 10,000 observations. So the lower graph is a logistic distribution graph, whereas in the blue, which is the almost upper graph, is the of normal distribution. So how is the estimation done? In estimation of both logit and probit is done through maximization of log likelihood of joint density as we give it. Fx is a logistic distribution in case of logit model and is a normal distribution in case of probit models as explained above. The optimal value of beta vector is the one which maximizes the log likelihood. Once the beta is obtained, the probability can be easily obtained through the respective density or distribution, as the probability of the area under the probability density curve corresponds to beta xi, or value obtained from the cumulative distribution corresponding to beta xi. So what is joint density? Joint density can be written as small f y given x and beta and is equal to phi I, which is a symbol for product, which means multiplication of f into xi beta raised to the power yi into 1 minus f xi beta whole raised to power 1 minus yi. If you take the log function of this, we get the log likelihood, which is denoted as ln L. It comes out to be equal to sigma, which is summation over I. I could take the values from 1 to n or 1 to infinity, and this summation is of yi into ln f xi beta plus 1 minus yi ln into 1 minus f xi beta, where in case of logit model f xi beta is nothing but is equal to 1 upon 1 plus e raised to power minus xi beta. So our log likelihood function comes out to be equal to e raised to power xi beta upon 1 plus e raised to power xi beta. Similarly, in case of probit model, we get capital F xi beta equal to x is equal to half plus bracket starts 1 plus ERF in bracket small bracket xi beta upon root 2. So a small bracket is closed and the big bracket is also closed, which is the middle one. The log likelihood is maximized and the optimal values of the coefficients are estimated. For details of this, you can also refer to Cameron and Trivedi written in 2005. So let's look at a graph. In this graph, you can see that we have the probability under normal and logistic distribution. Again, on the x-axis, we have the values of x, and on the y-axis we have their corresponding, you can say, probabilities or their density functions. Suppose that we want to know probability corresponding to beta xi equal to 1. This is the known shaded area under normal distribution in our graph under the TOBIT estimation. If we would have done logit estimation, then the probability would have been slightly lower, and the same can be seen from the probability obtained from the cumulative distribution as given in graph. So you can now look at graph where we have the probability under normal and logistic distribution, and you can compare this graph 5 with graph 4. The logit and probit could not be a better fit in many cases, but this certainly proves upon the two crucial shortcomings of the OLS estimation. In case of logit and probit, the predicted probability will not go outside the unit interval, that is the values between 0 and 1. Graphs shows the predicted probability from the three models. And second is that the rate of change of probability, which means the marginal effects, is not constant, which we would discuss in a slightly short time later on. So if you look at this graph, which is for our problem of hospitalization of diarrhea patients versus age, where if you remember we said if the patient is not admitted we have value 0, if admitted we have value 1. So the values are between 0 and 1. And if you look at the three graphs which are for the linear probability model, we have for logit model and probit model, then you can see for linear probability model the curve is going above 1, whereas in the other two cases the curve is within the limits of, or both the curves are within the limit of 0 and 1. So that way you can see the advantage of logit and probit models over the linear probability models. Having understood this, let us now try to understand a concept known as odd ratio. The coefficient beta can be understood in terms of odd ratio in the case of logit model. This is defined as phi I is equal to f xi beta, which is equal to epsilon raised to power bix upon 1 plus epsilon bix. Define odd ratio OR as phi I upon 1 minus phi I. And this gives us the odd ratio as phi I upon 1 minus phi I equal to epsilon raised to power beta I x. If you take the log of this, then ln phi I upon 1 minus phi I comes out to be ln OR, which is odd ratio, and this comes out to be equal to beta I x. From above we can deduce that change in log odd ratio is beta j when xj changes by 1 unit in case of logit model. In case of probit model, when xj changes by 1 unit, z values changes by beta j unit, and explaining this is a bit difficult in comparison to the logit model. Therefore, let us try to understand now from this the impact and the estimation and calculation of marginal effects. Marginal effects are nothing but instantaneous rate of change, and you compute them for a variable while all other variables are held constant. So marginal effects are basically the change in probability due to change in xj and can be denoted as derivative of phi I upon derivative of xj. Calculating marginal effects is very straightforward in case of OLS estimation, as beta j itself represent the marginal effects. Remember, in case of OLS estimation, the rate of change of probability is constant. But in the case of logit and probit model, calculating marginal effect is not so simple, and you will find that the marginal effects are not that straightforward, as the change in probability due to a change in xj is not constant. The approximate marginal effects at the mean value of the covariates are given by which is derivative of phi I upon derivative of xj, or derivative of phi I with respect to derivative of xj is equal to beta j into phi I into 1 minus phi I, or this symbol you may also call it as pi I. For binary independent variables, marginal effects measure discrete change. That is, how do predicted probabilities change as the binary independent variable changes from 0 to 1. For categorical variables with more than two possible values, which means, say for example, the religion, the marginal effects show you the difference in the predicted probabilities for cases in one category relative to the reference category. So for example, if religion was coded as 1 for Catholic, 2 for Protestant, and 3 for Jews, and 4 for others, the marginal effects for Protestant would show you how much more or less likely Protestants were to succeed than were Catholics. The marginal effects for Jews would show you how much more or less likely Jews were to succeed than were Catholics, etc. So keep in mind that these are the marginal effects when all other variables equal their means, and hence the terms MEMs. The marginal effects will differ at other values of x. So marginal effects for our example is given in our table 1, where we have the models as logit, probit, or linear probability models, and we have the marginal effects of A's. And for our model, you can see these values are different. For logit, it is minus 0.029551. For probit model, it is minus 0.028847. And for linear probability model, it is minus 0.023661. Now, this table gives the marginal effects at means. The marginal effects at means are lowest for linear model, and it is same for all values of A's as shown in graph. The marginal effects of logit and probit models are almost same, and first decrease with A's and then start increasing. This makes sense in case of our example, as in the beginning the marginal effects of A's decreases in beginning and becomes negative, but after a certain age the marginal effects of age start increasing and becomes positive. This is very clear from this graph, where we have the marginal effects of age versus age of logit and probit and the LPM model. So we have marginal effects of age, and we have these three different curves for these three different scenarios. Let's take some examples here. Suppose that we are interested in the factors that influence whether a political candidate wins an election. I'm sure you know there are only two possible outcomes, win or lose, and these outcome response may be denoted as a binary variable with 0, 1. The predictor variables of interest are the amount of money spent on the campaign, the amount of time spent campaigning negatively, and whether or not the candidate is an incumbent. Similarly, we can take another example, example 2. A researcher is interested in how variables such as GRE, which is graduate record examination scores, or GPA, grade point average, and prestige of the undergraduate institution affect admission into the graduate school. The response variable, admit or do not admit, is a binary variable. So you are either admitted or you are not admitted. These are our two possible outcomes, which we are defining as a binary variable. Now, this data set has a binary response, where outcome or dependent variable is called admit. The data set can be obtained from a website which we have of UCLA, which is University of California, Los Angeles. So there are three predictor variables which we have taken here: GRE, GPA, and rank. And we will treat the variables GRE and GPA as a continuous variable, which means it can take any possible value. The variable rank takes on the values 1 through 4. Institutions with a rank of 1 have the highest prestige, while those with a rank of 4 have the lowest. So we have a kind of a ranking from 1 to 4. Now we are interested in understanding how GRE, GPA and rank affects the probability to admit of a child or a student. So we estimate all the three models and the output is given in the table where we have these regression results on the basis of the three models which we have understood so far, the LPM model, the Latent model and the TOBIT model in the three columns. And on the left hand side in the first column you can see we have GRE, GPA and we have the rank and we have four possible values: first rank, second rank, third rank and fourth rank. Then we have the constant and we have the n, which is the number of observations in this case, and is equal to 4000. The results are presented before you in this table and we can see the interpretation. Along with all the values of the coefficients, we have given the t statistics in the parenthesis to understand whether they are statistically significant or not. And the p-values are also given and they are denoted by a single star, double star and 3 stars. Single star is where p is less than 0.05, double star is where p is less than 0.01 and 3 stars are where p is less than 0.001. I am sure all of you would understand this is for 1%, 5% and 10% level of significance. So in the table we see the coefficients and their associated p-values. Both GRE and GPA are statistically significant, as are the three indicator variables for rank, which are significant in all the three models. Now positive coefficients, I am sure you all understand, imply that increase in the predictor increases the probability. The higher is the GPA or GRE, higher is your probability of being admitted. The logistic regression coefficients give the change in the log odds of the outcome for a 1 unit increase in the predictor variable, while TOBIT regression coefficients gives change in Z value. So for every 1 unit change in GRE, the log odds of admission versus non-admission increases by 0.002. For a 1 unit increase in GPA, the log odds of being admitted to graduate school increases by 0.804. The indicator variables for rank have a slightly different interpretation. For example, having attended an undergraduate institution with rank of 2 versus an institution with a rank of 1, it decreases the log odds of admission by 0.675. The regression coefficients in the other models can be explained similarly. Let's now look at the marginal effects at means. We have table 3 for that, in which we have the LPM model, again the Latent and the TOBIT models, and we have these marginal effects of GRE, GPA, rank 2, 3, 4, and rank 1 is our benchmark category. This above table gives the marginal effects at mean values of the predictor values. These marginal effects have been calculated at the mean values of the given and other predictors. The marginal effects must be used to calculate the change in the probability for small values of change in predictor variables. For large change in the predictor variables, it may not give the accurate results. You have to understand this, which can be shown on a graph and basically shows you all these three different models and their predicted values. So we have predicted probability versus GPA for rank 4 in this diagram for all the three models. And you can see the differences in the predictability done by these three models. Similarly, we have graph which is for rank 4, again for predicted probability versus GRE. So earlier we had GPA, in graph 9 we have GRE. So having understood all this, let us say that the above graphs 8 and 9, they gives the predicted probability for admission at GPA and GRE, as GPA and GRE score varies for rank 4 while other variables are kept at their mean value. This means in graph 9 it gives the predicted probability of admission at different values of GRE score for rank 4 and mean value of other predictors. Once again, I am sure you can see that the linearity in the OLS predicted probabilities and non-linearity in the predicted values of logit and probit models. So I am sure this is clear that how OLS gives you a linear kind of a relationship, whereas the logit and probit models, they give you non-linear relationships. That is the major difference between these models. So the important thing to see from here is that the predicted probabilities from both the logit and probit are almost same, and the difference arises for very low and high values, and that is because of the differences in the tails of the logistic and normal distribution. At mean values of GPA and GRE, even the OLS predicted probabilities are same as of logit and probit models. This makes choice of a correct model a tough choice, as to be explained later on. So in graph we have the marginal effects of GRE versus GRE for rank 4, which means one is total GRE and the second is GRE for rank 4. And similarly in graph we have the marginal effects of GPA versus GPA for rank 4 for a comparison. The above graphs 10 and 11 give the marginal effects of GRE and GPA, as GRE and GPA score varies while other variables are kept at their mean value for rank 4. So once again we can see that number 1, that OLS marginal effects are constant. Number 2, there is non-linearity in the marginal effects of the logit and probit models. The important thing to see from here is that the marginal effect from the logit model is always lesser than the marginal effect from the probit model. At the very high values of GRE and GPA, the marginal effects from the logit and probit almost becomes equal to the marginal effects of OLS. So we have understood the differences between these three. Let us now move on to a very important area known as goodness of fit. The traditional measure of goodness of fit, which is R square, used in the case of OLS regression, is not applicable in the case of logit and probit models. The OLS estimation is based on minimizing the residual sum of squares, whereas logit and probit models are estimated through maximum likelihood, which is an iterative process. Therefore, in the case of logit and probit, we have measures of goodness of fit known as pseudo R square. These measures also lie between 0 and 1, and a higher value implies better fit, but they can't be interpreted as normal R square. We can explain the commonly used pseudo R square. The Efron's pseudo R square is equal to, or R square is equal to 1 minus sigma I from 1 to n yi minus phi I square upon sigma I from 1 to n yi minus y whole square, where phi I is the predicted probability and y is the mean. Similarly, we have another pseudo R square defined by McFadden's, and this is defined as R square is equal to 1 minus log likelihood full upon log likelihood intercept. Most of the statistical package reports log likelihood after estimation. We need to calculate two log likelihood, one without predictor and other with predictors. Once we have these log likelihood, we can use the above formula to calculate McFadden's pseudo R square. The log likelihood of the above model in our example with intercept only is minus 249.98826, and with predictors the log likelihood is minus 229.25875. So we get McFadden's pseudo R square equal to 1 minus 229.25875 upon minus 249.98826, and this comes out to be equal to 0.082921934. So we get this value which we can see from this formula. Now McFadden's adjusted pseudo R square is also defined and is equal to 1 minus log likelihood full minus k upon log likelihood of the intercept. This McFadden's adjusted pseudo R square is similar to adjusted R square of the OLS, and it's tried to adjust for number of predictors. Since in our example the number of predictors is 5, so we can also find out McFadden's adjusted pseudo R square, and I'm sure all of you can see that it comes out to be equal to 0.0629209995. Now similar to this, we also have Cox and Snell's pseudo R square, which is defined as R square is equal to 1 minus log likelihood of intercept upon log likelihood full multiplied by 2 divided by n. Now this ratio of log likelihood of intercept upon log likelihood full with power 1 depicts the improvement of full model with predictor variables in comparison to the model with intercept only. So the lower the ratio, greater is the improvement. The value of Cox and Snell's pseudo R square can't be 1, and that is what differentiates it with other measures. Similarly, we also have another concept known as count pseudo R square, which is defined as R square is equal to count upon total count. We have given you a count table where we have the values of 1 and 0, our binary variables. We have the counts of plus and minus values, and you can see in this table we have the total of the 1 counts and the 0 counts, and similarly the totals of the plus and the minus counts, and our total is 400 as we said earlier. Now after the estimation of the model, we can calculate predicted probabilities. Most of the statistical package offers the features of estimating predicted values after the regression model. Once the predicted probabilities are there, we will use these to construct a binary variable of 0 and 1. We choose a cutoff predicted probability of 0.5, and those having less than this value are given 0, and those get more than 0.5 are greater, and or which means they are greater than 0.5, they are given the value of 1. So once this binary is ready, we match this binary with the actual, and matched 0 and matched 1 are counted. We divide this count with total count to get count pseudo R square. Most of the statistical package offers count table, which is obtained from the statistical software. In this table, plus sign refers to the number of matches between original and predicted binary for 1, and minus sign refers to the number of matches between original and predicted binary for 0. Sensitivity is a proportion of the ones that are correctly identified, which is in this case 30 by 127, and is equal to 0.2362200472. Specificity is the proportion of zeros correctly identified, which in this case is 254 by 273 and comes out to be 0.93197279. The proportion correctly specified, also known as the count R square, is therefore equal to 254 plus 30 divided by 400 and is equal to 0.710. Similarly, we can have adjusted count pseudo R square, which is defined as R square is equal to count minus n upon total count minus n. The count r square can be misleading values under certain circumstances. So in a binary model, one can easily categorize at least 50% of the cases without the use of predictors, variables, by choosing the most common outcome. The count r square needs to be adjusted by the largest row marginal total. In our example, the adjusted count r square is equal to 30 plus 254 minus 273 upon 400 minus 273. Now this comes out to be 14 from the numerator and 127 from the denominator and is equal to 0.087. We can say the adjusted count is percentage of match above what can be done by guessing. So let us now summarize what we have learned in this module. What we have learned is that LPM avoids the risk of misspecification of the link function, that is whether logit or probit to use. The estimated marginal effects from the LPM, logit and probit models are usually very similar, especially if you have a large sample size. There are complications with logit or probit if you have endogenous dummy regressors. In the linear regression model, certain types of misspecification has only mild implications of our inferences. However, these results change if the model is nonlinear in the parameters, a fact that is well known. More specifically, these results change for the worse in the context of such linear models as logit or probit or TOBIT, etc. The choice between the logit and probit is a tough one, and it mainly depends upon, like any other econometric modeling, on knowledge of the response distribution, theoretical considerations, and empirical fit to the data. From the point of view of your substantive theory, if you are thinking of your covariates as directly connected to the probability of success, then you would typically choose logistic regression because it is the canonical link. However, you will find that if you want to understand and take the following example, you are asked to model high blood pressure as a function of some covariates. Basically, we are interested in understanding how various characteristics affect blood pressure. Now, blood pressure is normally distributed in the population. It seems prima facie, and even medical evidence suggests something similar. But during the experiment, we recorded the blood pressure as a binary variable, that is 1 for high blood pressure and 0 for normal blood pressure. What we are observing as binary variable is actually observation from a hidden Gaussian distribution, and in this case, probit would be preferable a priori for theoretical reasons. Lastly, note that the empirical fit of the model to the data is unlikely to be of assistance in selecting either logit or probit, as the shapes of the link functions in questions don't differ substantially. But still, we can test whether logit or probit is a better fit by various post-estimation model selection tests.